Hi everyone, I'm Chelsea Finn, and I'm thrilled to be introducing and moderating the Q&A for Alyosha's keynote. As a reminder, please ask questions by entering them into Rocket Chat, and please enter your questions both during the talk and after the talk. Alyosha is a professor of computer science at UC Berkeley and a member of the Berkeley AI Research Lab. And prior to that, he was on the faculty of Carnegie Mellon University for 9 years and also has been affiliated with INRIA and University of Oxford. His research spans computer vision, computer graphics, and machine learning, and his work has been recognized with numerous fellowships and awards, most recently including the ACM Prize in Computing in 2016 and the Diane McIntyre Award for Excellence in Teaching Computer Science in 2019. Beyond his official bio, you may not know that he is also an avid hiker, and his PhD dissertation includes a 7-page guide to hiking in Berkeley, complete with sunset walks, purpose hikes, and ground hikes, some of which I've also enjoyed myself with Alyosha and folks at Berkeley. But I would say that Alyosha's perhaps most striking characteristic is his wisdom coupled with his humility, and Alyosha has assured me multiple times that there's really a large degree of luck in doing research, but his remarkable contributions to computer vision, to computer graphics, and machine learning really make it clear that he hasn't just gotten lucky, and I'm really looking forward to his talk. Let's get started.
Good afternoon. So let's start with a very basic question. Why do we want to use self-supervised learning? And the common answer is, well, because labels are expensive. And that's not a bad answer, but it's not my favorite answer. Why? Because, frankly, if you're a big company and you have a very clearly defined task that you want to solve, you can just spam your way into the solution. You can hire enough people to do the labels, and frankly, there is so many of us on Earth that we can just self-label most of the things that these big companies are interested in. Even things like self-driving cars. There's still going to be way more people on Earth than there are street signs in all the roads in the world. So this is not easy to do, but it's not impossible. Okay. So in this talk, I want to tell you about the reasons I'm very excited about self-supervision. Okay. And I'm going to talk about each one of them and give you an example work from my lab on this. And none of them are really figured out. So this is all kind of work in progress. So please treat it as such. And so my reasons are, we want to do self-supervision to get away from semantic categories, to get away from fixed data sets, and to get away from fixed objectives. And I'm going to tell you about this. So let's start with the first one, semantic categories. So what is the problem with semantic categories? Well, here is a couple of categories, chair and city. And these are just images that we give to our classifier, and we hope that it will understand what a chair is, for example. But think about it. This is really unfair to expect the computer to figure out what is in common between these examples of chairs, because visually there is basically nothing in common. Because chair is a category that's functional, that's based on affordances. And for us, we can see the similarities because we have experience with, squeezing our bottom into various things that could serve as chairs. But for a computer, just seeing this as images, it doesn't have any of this information. And so it really does not know how to connect these instances together into a category. The same thing for cities. So on the left, you have Pittsburgh, on the right, you have Paris. And, by some fluke of the English language, these are called by the same noun, city. But there is really nothing in common between them. You can say, well, they both have buildings. But look, the buildings look completely different. And the windows in the buildings look completely different. There is very little that's in common here. And so what the computer is going to do is just try to remember every instance by itself and hope that at test time it will see something that's similar to what it has seen at training time. But, are they really understanding the deep concept? Are they really able to generalize? Probably not, right? And I think the problem here goes much, much farther back and goes back to Plato and Aristotle and their whole classical concept of categorization. This idea that categories are defined by a list of properties shared by all elements in a category, that category membership is binary, that every member in the category is equal. And the thing is that humans, we don't do that. That's actually not how we process categories. And famously, Wittgenstein and Eleanor Roche have argued that this is not how humans work. Wittgenstein's very famous example is to say, okay, give me a list of properties shared by all games and not shared by any non-games. And turns out it cannot be done. It's just impossible to do because we don't categorize this way. This whole idea that the membership is binary, that all the members of a category are equal, not really. For example, chicken, it's a bird, yes, but when you think of a bird, you don't think of chicken, you think of an eagle or sparrow or things like this. Categories are language dependent. So, for example, in Russia, we don't have a single word for chair. We have three: stool, kресло, табуретка, and so it seems like if you're a Russian programmer writing a object detector, then you can get completely different results from somebody working in English. That doesn't seem right. So really, in the 20th century, researchers started thinking that instead of this top-down categorization paradigm, maybe the right way to model human cognition is to think about categories as bottom-up associations. And this is where Eleanor Roche came up with her prototype theory, which is basically kind of your clustering instancing together into these prototypes that become these proto-categories. Other psychologists have went even farther and said, okay, maybe we just don't even need to cluster. Maybe just every instance is connected kind of at runtime to create kind of on-the-fly categories. This kind of exemplar-based theory. I like what neuroscientist Moshe Bar says about this. He says, ask not what is it, ask what is it like. So this idea of connections, of associations, I think is very, very key here. And so we were very taken with this works, and we early on really tried to kind of to operationalize that in computer vision. And so this is my old work with Tomasz Milashevich, my early grad student. And so here we said that, okay, can we create these bottom-up categories basically just from visual information alone by merging together instances, by learning these, per example, distances. So, for example, for this particular car, can we find what it should connect to? What other cars should be in the same kind of visual category with it? And so here the idea was that we would kind of separate the things that belong to this particular example from things that don't. And we divided things into three different topics. So there was the similar things that were similar, basically other cars that look similar. There was things that not similar, which is objects that are not cars. And then we also added another category, the don't cares, which are also cars, but probably visually shouldn't be in that cluster. Okay, and that allowed us to basically do some nice kind of retrieval results showing that we can actually capture these visual similarities in a good way, but it still used categories in some way. And so in the follow-up paper, we decided to just get rid of categories completely and say, okay, can we basically define every instance by how different it is from all the other instances in the data? Okay, so this kind of one against all classification. So you define yourself, but by what you are not, rather than the company you keep. And we showed that basically an ensemble of these kind of one against all classifiers was working just as well as a classical category-based classifier. And we also showed that you could do it for image retrieval, to kind of use this to kind of to find out what a query image, how does it connect with the rest of your data set, and order the data based on it. So this was, we were very excited by that, but of course then deep learning happened, and we tried to update us to the deep learning era, but we somehow didn't manage to make it work. But another group, the Savitsky et al., they did manage to make it work. This is the exemplar CNN paper. And the way they made it work is that instead of doing one against all classification, they made an actual class out of the positives by doing data augmentation. So they took a single positive image, but then they created a whole bunch of pseudo-positives that were basically just variations of that image using the idea of data augmentation. And then it worked very, very well. And of course, nowadays, this whole area of similarity learning has been doing really, really well and getting some really nice results. And so basically the idea is you group the positives are all your data augmented versions of yourself, and the negatives is everybody else, and then you can try to kind of separate them. And of course, one of the reasons why there has been so much progress is lots of great improvements in the learning paradigm, especially the contrastive learning. Really, it seems to be kind of every couple of weeks there is more and more exciting stuff on arXiv. But I think another kind of maybe not really appreciated thing is that data augmentation has also been improving over time. For example, cropping turns out to be a very, very important data augmentation technique that hasn't been used in the beginning. So again, basically data augmentation is a way to start from an input image and create a little pseudo class based on that image by basically randomly creating versions of that image by changing the color, cropping, flipping, blurring, etc., etc. But the thing is that the choice of which data augmentations to use is itself a kind of supervision. So in a paper that is presented in this conference, what we show is that for different types of tasks, you need very different types of data augmentation. And so the human choice of which data augmentations to use actually plays a huge effect on the final performance. And so this is a little bit unfortunate because, self-supervision is all supposed to be, getting away from the humans. And here we are sneaking the humans back in some way. And so we were really excited, thinking about how we can kind of get rid of this human supervision. And we get excited about using video as this kind of automatic data augmentation depository. Because in a sense, you can think of correspondences across frame of a video as being the key information that you need to find what connects and how visual data can vary and what connects different parts of the visual data together. And I think it's important to note that this is this idea of common fate. This idea of temporal correspondences is something that infants, this is the first thing that infants learn. This is the first thing that basically bootstraps the whole visual system is this idea of common fate correspondences. And then from that, they learn things like contextual information and grouping and segmentation and things like this. And so that's what we wanted to do. And of course, there's a lot of work on learning representations from video, but most of it has been from either using full frames for learning the representations or using some sort of off-the-shelf trackers. And so what we did in last year's NERPs is to try to see if we could get a good correspondence and learn a good feature in a self-supervised way using what we call the contrastive random walks. So the idea is basically the following. So imagine that for now that you actually have correspondences of patches in your image. So for example, you're told that this patch over there goes to that patch over there in the first frame. Okay. Well, so you can do your distance learning right now because you can say that this blue and this green are the positives and everything else is negatives. Okay. But you can do a little bit better because you also have the second frame. And you can say, well, the blue patch, it probably went through that fourth patch in the second frame before it got to the green patch. And so that intermediate patch should also be kind of a latent positive. It's a latent view that we didn't have to label, but it's kind of implicitly a positive data augmented data. Okay. Now, so we get a little bit of free data augmentation for ourselves, but we can do even better because now we can say, okay, forget about the labels, but instead let's take our little video segment and let's make it into a palindrome. Let's basically play it backwards. Okay? And now we have this kind of a cycle in time. And now we basically, all we want to do is that for our blue patch, we need to basically get it back home to where it started with. So now we don't need correspondence, but we can get all of these intermediate patches that it passes through, that it likely passes through, to act as our data augmented positives for free. Okay, so basically that's the story. So we take a video, we turn it into a palindrome, and then we basically make it into a graph. And then we perform a random walk on this graph, one frame at a time. And this random walk is steered towards ending up at the target frame, this green node of the target frame, which is exactly the same node as what we started with, because this is a palindrome. Okay, and so now we have a very nice contrastive problem. So basically, we need to get to the green node, as our positive, and not get into the red ones, which are our negatives. But the nice thing is that actually in every single frame, we also have a contrastive problem that's implicit, that's kind of automatically induced by this random walk. And so we actually get to have a lot of positives and negatives, and they're all, they're probabilistic. We don't have to force them to be one or the other. And this actually turns out to be a very nice way to learn feature representations. And so I'm going to just show you some examples. So if this is a tracking result from the prior work, and here it is for our method, and you can see that it's much more stable. And we also have good numbers compared to even things like ImageNet pre-training or more general methods like Molecorns and things. And you should read the rest of the paper if you're interested. Okay, so the second reason I'm excited about self-supervision is getting away from fixed data sets. Okay, so what's wrong with fixed data sets? Let's start with a real world motivation. If you're a biological agent, you never ever see the same data twice. Like if you're a human, you'll never see the same thing ever again. Just once in your lifetime, right? Every next time it's going to be a little bit different. It's not going to be exactly the same ever, right? And so for every new piece of data, you see it just once. You first treat it as a test sample. So you decide what to do based on that piece of data. And then, unless you die somehow, if you make the wrong choice, then you can get to also use that piece of data as training data for what comes next. But you'll never, ever experience it again. Okay? And in machine learning, we don't really do that. Usually what happens is that we see the same sample over and over again, and so that's kind of the weird thing where it basically encourages memorization, and it might discourage generalization because you don't need to think what is going to happen if you don't, if you never see things that are exactly the same. And this, by the way, might explain why data augmentation works so well. Maybe part of it is because you're actually augmenting the data. On every round you do a different augmentation, so you're actually kind of getting away from that a little bit. But so the only reason for fixed data sets really is basically the annotation expense. You don't want to have a huge, infinite data set because you need to label every piece of it. But if you're already using self-supervision, then basically there is no excuse to ever use data, because data is basically free. The annotation are expensive. The data is free, so we should never ever do multiple ad hocs. We should just be like biological agents and just use data only once. And so this is kind of the story that we had in mind. So basically think about it like if you have a training set, we know that splitting it into a training set and a val set, improves performance, right? But imagine that we can basically push this farther and think about, okay, you have some data that you have already seen, that's kind of your training set, and then you get a new piece of data. So you can think of it as kind of your validation set. So you first test on it, and after you've tested it, then you can basically update your model using that, and then you can move over to the next piece of data and the next piece of data, and you could basically do this continuously. The only thing is, of course, you need to have either infinitely many labels for all this data or self-supervised learning. Okay, and so this is one of our works that kind of played around with this idea. We call it test time training, and in here it's for the purpose of generalization on distribution shifts. So imagine that you have you're evaluating your pre-trained model on a distribution queue that's maybe is somewhat different from what you trained on, right? So now we get one sample from Q, the sample X, and that sample X actually gives us a little hint about what Q is all about. And so the idea is that we can adapt our model, make our model dependent on this test sample X to hopefully perform better at our task. So it's kind of like we have a one sample learning problem, but of course we don't have the label, but we do have self-supervision. And so the idea is very, very simple. So we train a network with two losses. One is your standard loss of the task at hand, like classification, for example. And then at the same time, you also have a self-supervised loss. So for example, predicting the orientation of an image. Okay? And so at training time, you train with both of those losses at the same time. Now, test time comes. You don't have the label anymore, of course, but you can still do your self-supervised task. So you do the self-supervised task, and if you're wrong, then you can do a little bit of learning, a little bit of adapting of the model so that your model does well on this new test sample X for the self-supervised task. And the hope is that since those models are correlated, that should also adapt you for the main task. Okay? And then you make your prediction for the main task. And the hope is that you are going to do better. And indeed, we can see that, for example, here you have a model and it thinks that this image is of a dog. But then as we adapt it over the iterations of the test time training, you can see that the dog is less confident and the elephant becomes more and more confident. And the nice thing is that you can do it one sample at a time and just throw away the model and then start over, or you can think about it in an online version where you can say that the samples they come from a same distribution queue, or it might be coming from a smoothly changing distribution. And that way, if you want to think about it this way, then you don't throw away whatever model you adapted, but you just keep adapting every new sample, adapted a little bit more. So this is kind of a way to deal with smoothly changing data, which I think is most of the data in the world is actually smoothly changing. And so this is kind of an example of using this, and here are some of the results and some of the examples, but you can look at the paper yourself. In this conference, we have kind of use the same idea for a follow-up work applying this to policy adaptation. So basically, you train something at training time with RL, but also having a self-supervised task. And then when you're ready to deploy it in a new environment, you don't have your RL loss anymore, but you can still use your self-supervised loss to adapt your policy. And so here is an example of kind of training and simulation and testing in the real world, and you can see that it's able to do this. Okay. Finally, let's get to the kind of the most crazy direction I'm excited about: self-supervision as a way to get rid of fixed objectives. So what's wrong with fixed objectives? As many of you perhaps in high school, I was super excited about genetic algorithms, genetic programming, all that stuff. It was like, wow, it's all like biologically inspired evolution stuff. And then I kind of got, disillusioned with it, right? Because really I realized that it's just another way to optimize the same objective function, and it's not even a very good way to optimize things, right? And after reading a lot of biology books, I realized that the magic of evolution is not in the kind of details of the optimization. It's actually in the fact that it doesn't optimize any objective, right? The objectives actually emerge on their own. Evolution is not actually optimizing anything, right? You can say, well, we're optimizing survival. No, it's not really. In fact, even death is an emergent property. It's not built into evolution. It's a fascinating subject, but basically, can we get some of this magic into our models? How can we get emergent objectives ourselves? And of course, if you ask the biologists or you can ask the economists, they give you the same answer: arms races. So I can understand the economists. I came from the Soviet Union, and when I was growing up in the 80s, there was basically no food in the stores, and huge lines, no food. And when I got as a teenager to America, and I went to the supermarket, I was shocked. I couldn't believe it, like so much stuff, and I really didn't understand. I thought, okay, we Russians, we have a lot of famous physicists, mathematicians, composers, writers. Not the dumbest country in the world, but why can't we get food in the stores? And then I realized that really the issue seems to be the idea of this planned economy, this famous 5-year plan that basically all Soviet economy worked on these plans, where you predict kind of a fixed objective and then you go for it. And so here is an example I like to show. This is the HP calculator, 1973, and this is the Russian version of it, Electronica DD from 1973 also. And the socialist calculators are their biggest calculators. Basically it's like a cash register. So why did that happen? Why such a big disparity? Well, it's because 5 years earlier, the Soviet planners said, okay, we need the calculator to calculate things, and that's the goal, right? We just needed to calculate. Nobody was thinking about putting things in your pocket. And HP probably did the same thing too. But HP had other pressures. It needed to compete with other companies, so it needed to somehow make their product cheaper. And how do you make things cheaper? Well, you make it smaller, so you use less materials, okay? And so HP was also slowly making it smaller and smaller and smaller, until at some point they realized, oh my God, it's so small, we can actually put it in our pocket, and it could be a pocket calculator, right? And so that's basically kind of an emergent objective that got created just because of the arms race. And of course, in the planned economy, there was no need for this, because it does calculations, and who cares if it's the size of a cash register, right? And so these emergent objectives, they're actually really, really powerful for development. And so How can we set up arms races? Well, we know some examples of these arms races already. So, for example, self-play, right? It's kind of a symmetric arms race of agent versus itself. Unfortunately, in practice, you still kind of have to specify the final objective. So there's a limit to kind of how crazy it can go. It still kind of has an objective it tries to achieve. GANs are asymmetric. So you have a generator and you have a discriminator. And, ideally, in an ideal world, basically, the discriminator could get really, really clever and the generator could get even clever and then could go on forever and ever, this kind of this arms race. Unfortunately, in practice, the discriminator ends up dominating the generator pretty early on. And so this explosion of creativity doesn't really happen, at least currently. So one thing that I'm very excited about as a mechanism of setting up arms races is kind of having this goal of prediction as a meta objective. Okay, and so the idea here is that the world is the adversary. So it's kind of an asymmetric thing where you have your predicting agent, and that predicting agent is competing against the complexity of the world that does not necessarily wish to be predicted. Okay, and the nice thing is that if it all works out, it's open-ended, because in a complex enough world, one can always predict further. There's no limit to how smart of a predictor you can be. Okay, and so this was our kind of first attempt at trying to do something like this. We call it a curiosity-driven exploration by self-supervised prediction. And basically, the idea was to start with an agent playing a game of Mario, and so you have the inputs are the pixels of the video, and the actions are the buttons, right? And the agent doesn't know anything else. There's no goal, there is no score, nothing, right? So, but we made the agents be wanting to predict what's going to happen. So it's a crazy predictive agent. So the agent wants to always predict what's going to happen if it does a particular action. So I press a button, what's going to happen? Press another button, what's going to happen? What's going to happen, right? And then it's basically going to always try to predict things before they actually happen. So let's say you think what's going to happen if I press up button. So this is the prediction, and then you actually execute it, and then you say, oh, look at this, my prediction was correct. Good. Okay. But sometimes the prediction is not going to be correct. Okay. And so then we define curiosity as failure to predict. Is when the prediction error was high, we define this to be high curiosity, which is, wait a minute, my current model doesn't really explain the world. Maybe I want to explore this and investigate this further. And so basically the idea is this kind of a arms race between the prediction model that is trying to predict the consequences of its actions. If it has a good prediction, that's fine. But if it has a bad prediction, it becomes excited because it becomes more curious about kind of exploring this further. And so we're basically getting this kind of an ongoing battle between the predictor and the curiosity. Okay, and so the predictor wants to be really good at predicting the world, and the curiosity moves the predictor around in the places that it's bad at. Okay, and so just doing that using basically no external rewards, just this curiosity, we get rid of the score, and then of course, at the start of training, nothing really happened, and then after a while of this training, you can see that the Mario basically just starts moving through the maze, and it starts to kind of emergent behaviors are created. He's basically killing the enemies. He's kind of moving through. He's not dying, because dying is not interesting, right? Dying means you have to start from the beginning again. And so basically, this is kind of exciting way when you can get some kind of emergent behaviors maybe to create and to have. And here we have an example of two curious agents playing with each other, and you basically get to kind of, it creates a rally, because basically, the most curious thing is to keep the ball going, even if you're not scoring that many points. Okay. But of course, this is all very kind of preliminary, and there's still a challenge to actually trying to do this in the real world with real robots. Okay, so in summary, why am I excited about self-supervision? I'm excited because it's a chance to get away from semantic categories and go towards data-driven association. It's a chance to get away from fixed data sets and think about ways that you can learn continuously in a kind of lifelong learning setting. And third, because it's a chance to get away from fixed objectives and maybe have objectives emerge on their own. Okay, so none of this is really at the point where I can declare success, but I feel like these directions are very exciting, and I invite you guys to think about them, and I think that there are interesting insights to be gleaned from these directions. Thank you very much for your attention.
Thank you so much for the amazing talk, Alyosha. I'd like to start off actually with a fairly general question before moving to the questions in the chat, which is, you talked a lot about kind of moving away from fixed objectives, from fixed data sets, and from categories. I'm curious if you have thoughts on how we should evaluate a self-supervised learning system and whether or not it's possible to move away from those things in evaluation, or if we should be evaluating them in terms of these kinds of categories with fixed data sets.
Thank you, Chelsea. Yeah, this is a very good. Well, okay. First, I want to apologize for the kind of muffled recording. This is the COVID times. And yeah. So, if you want to, you can hear the. I think the sound is better here. So if you didn't understand something, just ask clarification questions. Yeah. So I think the question of evaluation is an interesting question, because as I can tell you, kind of the perspective in computer vision. So when I started in grad school in late 90s, there was no evaluation. The joke was that CPR paper with one image is called a hack. If it has two images, it's an algorithm. If it has three images, well, it's a framework. So evaluation was all, you just look at a couple of images and that's it. And then kind of computer vision went into this kind of over crazy data set a decade in the 2000s. We made a lot of progress because we could actually evaluate what we were doing, not just eyeball it. But I think we also kind of got maybe a little bit too paranoid about always worrying about the data sets. Because if you look at people like political scientists, for example, or various kind of statistical ways of evaluating some model. Those people are living in a real world. They are doing polls of who is going to win the next election, and every time they're sampling a completely different subset, and they're computing some statistics over that subset. The subsets are not the same; they're always different. So there is always, of course, going to be some inherent issues with going from one sample to a different sample. But they're okay with it. There's error bars, and you just that okay, your error bars are not going to be super tight. They're going to be kind of wide, but it doesn't stop them in their tracks. I mean, look at the financial people, right? They're still predicting the stock market, even though every time they make the prediction, everything is different. So they if they worried about not being able to evaluate things consistently, they would not be able to make any progress at all. So I think we should just not worry too much about doing evaluation in this kind of on a rolling basis, kind of an online evaluation, where we have every time we have a model, we just download the next 24 hours of some data source, and then we compute it, do evaluation on there, and we get some numbers. Yes, it might not be the same as the number we got last time, but we have statistical methods to get the error bars and to figure out how significant that result is. And this is something that that people like Deva Ramanan, for example, were proposing for a while, to kind of have this role evaluation. I think that this is perfectly reasonable. Everybody else seems to be okay doing it, so maybe we shouldn't worry too much about evaluation.
Great, that makes a lot of sense. So there were some specific questions on the first work that you talked about with the random walks through a video. How do you actually follow the path through different frames when the patch isn't labeled in those frames? And if you apply this sort of cycle consistency between pixels instead of patches, does the performance drop?
Yeah, so what I did in this talk is I just did a little bit of kind of advertisements for some of the works, and if you want to know the details, I highly encourage you to go and watch the student Alan Jabari's wonderful NeurIPS talk that's on his webpage to kind of get all the details. But basically, the story is that you're doing this random walk from the beginning frame to the ending frame, which is also the beginning frame, so you don't actually need to have any labels. And your random walk is basically steering you to get back to where you started from, right? So that's your goal, is to get back to that same point. And that basically means that you need to find a path that will get you home, right? So essentially what you're learning is you're learning the feature that compares patches to each other, and you're optimizing for such a feature which will get you home for all of your training data. So that's basically the idea, that to get home you need to have good correspondence, and so you're learning a good correspondence. The second question about what happens if you're doing pixels instead of patches, that's a very good question. And in fact, if you are doing, if you're just doing pixels by themselves, then all pixels look like each other, because there's only 256 of them. So that's not going to work. But I guess maybe what you mean is, what if you do it densely, like basically at every centered at every pixel, like a patch centered at every pixel. And I think that's a very good direction. It basically then it turns into something like optical flow in computer vision. And indeed, we're right now working on trying to generalize that, to get this to work for in the dense regime. You can imagine that, it's computationally tricky, and also we need to get rid of some of the nasty ways in which self-supervision often starts to cheat. So like this, if you're working in self-supervision, you know that like 80% of your time is spent battling the computer cheating. And so this is the same thing here, but I think this is exactly the right direction, and we're basically we're playing with that, and I'm sure other groups are as well.
Great. So the next question is from Jivat, which is, what do you think about applying self-supervised learning to multimodal inputs, and can this be used to help in moving away from multiple choice questions like VQA, for example, towards more open-ended question answering and other more sophisticated and human-like task objectives?
Yeah, this is a good. So I think when you say multimodal, okay, I have lots of problems with multimodal, because first there is having multiple modes and also having multiple modalities, right? I am assuming you mean multiple modalities, and I think that you actually in particular mean the language and images modality, which I think is actually a very special kind of modality in this kind of multimodal era, because language is very, very high level, and pixels are very, very low level. And in my experience, it's often very hard to combine them together without somehow getting the computer to cheat, just because the language is just going to completely take over and often just not care not care about the pixels at all. It's kind of like all these kind of questions, like, how many apples are in this image? It's always two, right? Because if it's one, you wouldn't have a question like this, and three maybe is too many apples, right? So the kind of the prior often takes over. I like to think about the kind of the multimodal story from the bottom up. Let's start with something simple like vision and sound, right? Or vision and touch, or vision and, I don't know, smell, right? Things that are much more of physical measurement rather than result of millions of years of evolution. And I think in those content, in fact, if we'll go back to kind of the origins of self-supervised learning, one of the kind of key papers on that was by Virginia Dessau in the early 90s at NIPS, and her example was vision and sound as a motivation for providing a kind of learning, co-learning audio and visual at the same time, kind of by trying to kind of cross-predict each other. And we have done some work on this and other groups with vision and sound recently. You can look at Andrew Owens as one of the kind of key researchers in that area. Then there is, you can also think about something like, predicting color from grayscale as also kind of a multimodal kind of story. You have your roads and cones and your eye, and so you're predicting roads from cones and you're predicting cones from rods, and that also kind of teaches you to connect those sensors. And Chelsea, in fact, has been doing some wonderful work on sensory motor learning, which is, again, you connect the sensor and the motor kind of together. I think that that's where we should be starting, and then eventually when we get better and better and better, hopefully we will graduate to language. That's my kind of my agenda, to kind of to try to build this from the bottom up. Although, of course, there are people who are interested in trying to do it top down, which I think eventually we will meet somewhere in the middle. So I think both directions are valid, and hopefully we'll meet in the middle, and that's when everything will be solved.
Great. Next, let's go to a question from Ali, which is, in practice, wouldn't curiosity be another objective on its own? For example, bad prediction leads to learning for a particular task. And I think that they're alluding to how maybe it seems like it could just be thought of as a fixed objective rather than a changing objective. So can you comment on that?
Yeah, I call it, that's fair criticism. Yeah, I like to call it kind of a meta objective, in the same way as like adversarial loss is a meta objective, right? Which is that it's an objective that is able to adjust to the world, right? So like an adversarial objective, for example, in a GAN or something, if you give me better and better images, I'm going to start to nitpick better and better. So this is why GANs make for such great loss functions, right? Like a GAN gives you a learned loss function that is so much better than a fixed one like L1 or L2. And so to me, there is something different about that kind of objective than kind of a fixed one. But yeah, I mean, I guess part of it is kind of a definitional. In the same way, I feel like prediction is also kind of a meta objective because it's unbounded. Like in L1 or L2, you can get your objective to you can get your loss to be 0, right? You can basically be perfect, right? With something like prediction, you will never be perfect, because I will just ask you to predict farther and farther and farther, right? It's a kind of it's an endless game, right? As long as your world is willing to play ball with you, as long as your world has enough entropy, you should not be able to predict, infinitely far away. So you will never be able to satisfy this objective. The world will always eventually win over, right? And so I think that maybe is kind of the difference here, that you're trying to get you're trying to set up something that is not that has a way to go, that you will never get completely, you cannot overfit this objective. And I think maybe that's kind of the way to, but maybe there is a good name for it, I just don't know. If somebody knows, I would like to know.
Great. The next question is from Elliot, which is that the Russian versus US economy is a great example of the power of emergent objectives. Do you have any other pet examples of real world applications of emergent objectives beyond video games, and maybe something that's a stepping stone between video games and national economies?
Well, okay. I mean, evolution, of course, is the kind of the go-to example of emergent objective. I mean, look at us. Like, we are all made of one emergent objective over another. One thing I like to say is that we have emerged to have the brain because the world was changing enough that otherwise we would have emerged to have a lookup table instead and just did nearest neighbors. So yeah, I think there's definitely many kind of existent proofs. Now, going back to what kind of where we can actually get to do it, where it can be effective, I would be the first one to tell you that, yeah, video games, especially old video games, are definitely, it's a cute little trick, but it's not, that's not where the juice is. We need to try to get it to work in the real world. My former student Deepak Pathak, who was the first author on those papers, he has a couple of follow-ups. One of them, he tried to basically put curiosity on a real robot, and that did, that was interesting, but it was clear that there's still a lot that is not working, right? The problem is that in a video game, your output space is pretty limited. So you can be curious about everything, and eventually you will exhaust everything that you can do. In the real world, it seems like we need some sort of attention, right? We need to have a way to prioritize what we should be curious about and what it's not worth being curious about. And we still don't know how to do this. And this is there is some beautiful results from developmental psychology. I highly recommend you read some of Alison Gopnik's works on that, where babies and children are really good at being curious, exactly like they have this wonderful curriculum somehow built in, where they're curious exactly about the things that they are ready for. So you go to the store and you buy a toy, and it says 12 to 18 months, right? Or like 2 to 3 years. And this is amazingly accurate. You bring this toy, and if the kid is younger than 12 months, they will not look at it at all. If they're older than 18 months, again, they will not look at it at all. It could be sitting there forever. They will just not engage with a toy when it's not the right time. So it seems like one of the things we might be missing is some way to get this curiosity in some sort of like a hierarchical curriculum mode, where instead of just being curious about everything in the world, we can pace our curiosity in the right way. How to do it, I have no idea, but it seems like this might be the right direction to actually get it to be useful in the real world. And again, I think that somebody like Chelsea, you should actually have more more thoughts on this. In fact, why don't we turn this around a little bit and ask the expert? Chelsea, what do you think?
I'm not sure. I definitely think that in terms of exploration and so forth, we need algorithms that can better handle the richness of the real world. I think that when you're in a very narrow video game world, there isn't actually that much to explore. You but do have a much more constrained action space. And when we actually take these curiosity algorithms and put them onto real robots with vision observations and so forth, they really actually struggle to explore the things that in meaningful ways. They like to wave their arm, like the robot will like to wave its arm around a lot and do less meaningful things like opening drawers, interacting with objects, opening boxes, and so forth. And so I do think we need to, there's much more that needs to be done to build techniques that really explore it in ways that are meaningful. And how to actually do that, I don't know, but studying algorithms in rich environments is at least an important step, I think, towards that.
Yeah,
cool.
I think it's all about, run stuff on real data, and then at least you will know what the real problems are. And yeah.
Yeah, absolutely. So we have another question from Michael, which is, I really like the emphasis you've placed on moving away from fixed objectives. Unfortunately, a lot of our tools, both theoretical and empirical, focus on how to better approximate a fixed monolithic target function. But we can also all agree that this isn't how humans learn, and this isn't how an agent optimizing emergent objectives would learn. So with that in mind, do you think that achieving these kinds of emergent objectives will require moving away from the function approximation paradigm?
I'm not a theorist. I like to pester a lot of our resident Berkeley theorists with exactly these kind of questions. I think we don't want to be married too much to the formalisms that are in fashion in a particular day, and focus really on kind of what do we want to achieve. And it might be that, yeah, the function approximation formalism, it might be that it just a little trick, little update will actually just make it work and kind of in this more open-ended setting. Or maybe there will be a different formalism. And I think we just as long as we have an open mind, I think this is what this is what I've learned, over my couple of decades in this business, is that you don't want to be looking under the streetlight. You want to be looking at the place where you think the answer should be. And if it takes you away from the streetlight, well, it's going to be darker, but at least you're getting closer, hopefully, to the solution. So I don't know. I hope that when the theorists kind of appreciate the importance of looking in this direction, I think they will give us some beautiful new formulations, or maybe updated old formulations. I guess my job is to get the theorists to get with the program and to get them excited. And I think once we set our mind to it, I think there is a lot of things we can do. I mean, look at what happened last year with the vaccines, right? So I think that if we decide that this is a worthwhile direction, the new formalisms will come, the new ideas will come. I'm very optimistic about our ability to solve problems. I think maybe the hard thing is to state what the problems are, and once we state them, then everything is just gonna work. So I'm trying to kind of nudge towards this kind of problems, which I think are important. I might be completely wrong, by the way, but so do take it with many grains of salt. But to me, that seems to be the right direction to think about.
Great, and maybe let's have one more question, which is from Pedro. What do you think about explicitly formulating learning as a non-zero-sum game between subagents with different objectives, all of which contribute to the overall objective of fitness or something like that?
I'm not, okay, again, I'm really not a theorist. Like I was thinking of becoming a theater director or a psychologist. And so this whole computer science thing is all one big accident. So I'm not sure I can say anything very insightful on the formulation front. I'm a little bit unsure about the fitness thing, especially just reading a lot of biology. In fact, I very much like to recommend going back and just reading Darwin. The Origins of Species is an incredibly modern book that I loved. I loved it. I thought I would be very dated, but no, it's a beautiful read. And so I think that fitness is actually not the right story. I think it's not about fitness. Fitness is kind of like, it's not that evolution is optimizing for fitness. I think fitness just it's an emergent property of evolution, right? Evolution would also be just as happy with just a whole bunch of rocks just sitting there on the moon and just not doing anything. That's also fine, right? So I'm not sure we can formulate what is it that we want, because as soon as we formulate it, then there is going to be a shortcut to getting there, and then we will be done and we end, right? So I think it needs to be something that is somewhat different from that. But I mean, maybe the game theoretic formulation will maybe push it towards the objective, whatever it is, being pushed farther and farther back, and that way we'll avoid cheating. So I think this kind of adversarial setups are definitely or likely be part of the solution to avoid cheating. But what is the fundamental final loss that we want to write down? I don't know. I don't think it's that simple, but I don't really know the right question. Yeah.
Great. Thank you so much, Alyosha, for both the really great talk as well as the answering all of these questions. I think that we'll end it there. And I think that, yeah, everyone should enjoy the rest of the conference and also, of course, the workshops tomorrow.
Thank you very much. This was wonderful to chat with you.